Hello everyone, it's Chris from Mochrake here, and today I've got a video where we're going to do some audio synthesis using a programming language called Rust. Now, if you'd like to follow along with this tutorial, please take a look in the description. You should see some links to GitHub repositories and some other resources there. I'll just show you quickly what that looks like here. This is the repository for the example, FunDSP example in the Mochrake GitHub organization. And you'll see some simple instructions for running this. Now, we are assuming, right, that you have some experience with this type of programming language. We're using Rust. It's a systems level programming language. It's very performant, but it's quite technical. It's not like using something like Python, like some of my other videos are about. So it does assume some knowledge of that, and we're not doing a tutorial about this. Quite straightforward though. You can go and install it relatively easily on any system. So on Windows, on Mac, on Linux, no problem at all. If you visit this page, there's a few ways to install it, and then you'll be able to run the examples. And what you'll need is there's a little program that will be available in your terminal called Cargo, and we're going to use that to run everything. And the instructions you can see here. Now, let's get started with this. To do this tutorial, we're going to be using a library, an amazing library called FunDSP. It's not made by me, it's made by this guy, Sami Pertu. It is an audio synthesis library. It handles samples, it handles audio generation, effects processing, filters, all sorts of amazing things like this. You can use it to make interactive programs, so actual synthesizers, which you can send MIDI messages to and things like this. It has all the capabilities of doing this, but we're not doing that today. What we're doing is we're just getting it to generate a sound. And I'm going to talk about some of the infrastructure that's required, the sort of technical infrastructure that's required in order just to get a sound out of your computer. I'm not going to talk about the maths associated with digital signal processing because it's complex, and I'm not an expert in it by any means. I'm not going to talk about the sort of the Rust programming language here, but if you have any questions related to these things, I can try and point you in the right direction. But like I said, I'm not an expert in them. So let's get started. Let me go to my terminal here. And I have just downloaded this folder using, I used a program called Git in order to clone it down. This is version control software. If you've got that installed on your computer, it's relatively straightforward. If you don't have it installed on your computer, what you can do is, go here and you can copy this URL. If you've got Git, then you can git clone this. You probably know what that is if you do have Git. If you don't have Git, you can download a zip folder of it and extract it onto your computer. Now I'm using the terminal here. And I'm currently in this folder, and if we have a look inside, you can see this is all of the files. I'm on Windows. This is PowerShell that I'm using. I've got Rust installed on this system, so you'll need to have that set up as well. Like I said, it should work on Linux. No reason why it won't work on Mac as well. So these are the main folders, and the file that we're really interested in here is in this source directory, and this is main.rs, and this has all of our code for actually doing writing the synthesizer. Like I said, we're using FunDSP in order to make the sound. Now, let's have a look at that. I'm going to start a text editor. This is a terminal-based text editor called NeoVim. You can use anything you like. You can use Visual Studio Code. It's a really good text editor for making software, and you can download that, and there's lots of plugins for Rust and things that make it all a bit easier and more streamlined. That's a good place to start if you don't have any sort of preference on this to start with. So let's open this up, and you can see here, ignore the stuff that's going on down at the bottom. That's it just compiling the software and doing all sorts of checks and things. Yours might not look exactly the same as this. It's totally all right. It doesn't matter. Right, up at the top, you'll see that we're using, these are imports for different libraries. We're using two major libraries here, external libraries. So we're using CPAL, which is cross-platform audio library. This is a Rust library which is handles all of interfacing with your computer's audio devices, and I think it's cross-platform. It definitely works on Linux. It definitely works on Windows. Again, I'm sure it works on Mac. It probably works on. I've actually used it on Linux on ARM as well on a Raspberry Pi. So definitely is cross-platform, as they say. And then we're also using this FunDSP. FunDSP is the thing that's doing the maths to generate the actual sound. Right. This is going to be telling your speakers how they should be vibrating, basically, right? We're generating the actual audio with this. And then we're using part of the standard library. This thing's called an atomic reference counter. I'll get to that later on, but that doesn't matter too much, but it's part of the standard library. Okay, the most important thing here, right, is this main function. This is where we're going to start out. You can see it here. This main function is when you actually run the software, and you know what, we will run it in 2 seconds. This is where the program starts, right? And it just runs through this in order and does the things that we're asking. And there are three major elements to this, right? We've got the audio graph. This is the FunDSP data structure that can generate the sound, right? You can build this audio graph, and then when you extract sound from it, you get samples from it, then it'll recreate the sound that you're programming in. We've got run output, and what this everything inside this, it takes the audio graph and then it uses that audio graph to generate the samples, and it sends those samples to your speakers, right? To your headphones, to your speakers on your device. And then we also have this little section here, which is to do with keeping the whole program alive. And the program will run for 5 seconds and it'll exit. So let's show you what it sounds like without changing anything. This is how it will sound when you first download it. And we're going to use cargo. We're going to do cargo run, and cargo will be installed. This is for handling dependencies in Rust and packaging up libraries and binaries and all sorts of things. We're going to use this program. So it should be installed. Once you've installed it, it should be available on your terminal. I'm going to run cargo run release. Now the release flag here is important because we're doing audio programming. It's very computationally demanding, and so you need to have the release mode on. If you don't have release mode, then it's compiled in order for you to be able to debug it easily, and that makes it run much more slowly. So if you're having audio artifacts, just double check that you've got that release flag on. So let's run it now. Be careful. Watch the volume on your device. This is just going to make a pure sine wave at 440 hertz, which is an A or A4, I think, is on the MIDI note. Right. So here it comes. Be careful. Okay. Right. So we've got that. That's it producing some sound, and it's FunDSP that's doing the math in order to make that sound, right? And I'm going to show you how I do that, and I'm going to show you some more complicated examples. Now you notice when I've ran this that there are some warnings here. Don't worry about that. It's just because of the way that I've structured the code. It's telling me that I'm not using these functions at the moment, but I'm going to show you what the functions do, and you can swap them in and out. Okay, let's start back up the text editor and edit this main function and start going through this. So I'm going to come back to this audio graph later on. And this is the really fun and interesting part, right? That's actually to do with generating the audio. But we're going to go through the run output section to start with. And this is all the infrastructure that's required to actually talk and communicate with your computer's audio devices. If you are not interested in this part, because you really could just copy and paste this from my example, right? You don't need to worry about that too much. If you're just interested in the audio synthesis, then you could skip this section, and I'll put timestamps down below so you can do that. But I actually think that this is the most confusing part of using this library, or actually it's a very confusing part of doing audio programming at all, whether you use Rust or another systems programming language like C or C++ or D or something like this, right? Okay, let's go and have a look at this first, this run output. So let's go here. This is the definition of it. Let's pull it up here. You can see that I've added comments to this so that hopefully it'll make sense. These are comments when they start with a slash. These arrows that come after these here, this is my text editor giving me some extra information about what's going on in that line. Just ignore it. You might not have those on yours. You know, if you've installed it on Visual Studio Code or something, you can get that type of type hints that they're called. They're sort of annotations for your code. If you don't have them, don't worry about it, right? So it might look different, but it's not a big deal. Now, as soon as it gets to run output, what it does, it takes the audio graph. Now, this is the thing. Remember, I said that FunDSP were making this audio graph, and that's what generates the actual sound, right? That's what's doing the synthesis. It's the oscillators, it's the filters, it's the effects and whatnot that's actually making some sound. And it can use that to generate that audio, but it then needs to send that audio to your computer, the host device, right? So we're using CPAL to do that, and we're saying, okay, you take the default host, and that will be the computer that you're on. And then of that host, take the default output device. And this is the one that's currently connected. It's the one that when you start a game, it'll be the one that's like automatically it plays the sound through. Or if you're starting your DAW or whatnot, right? And you've not got your headphones plugged in and it comes out through your speakers, and then you plug in your headphones and then it'll come through your speakers. That's the default one, whichever one you're currently using. And you can change this generally in your operating system, right? Now, in Rust, there's this idea of something called options, and there's also results. I'm going to come back to this. You can see at the end here it says option device. And what it's saying here is that it may or may not find a default output device. And if it doesn't, we want to say, okay, well, we really were expecting to find something. And this is what this expect line does here. It's like, this might fail, and we want to know if it fails. And we just want to crash the whole program if it fails, because if we can't get the output device, it doesn't matter, right? We're not going to do the maths to generate the audio because we can't even hear the audio. So expect here is saying there might be an error. This might be where it is, and you should print this error string out. So if you see this, there's something's going wrong with the default output device. Feel free to message me in the comments if you're having an issue like this. I'll try to answer it if I can. Then once you've got the device, so that might be that Realtek audio or whatever it is that might be your sort of default sound device, or it could be an external audio interface, or who knows what. Once you've got that, we also need to get some config for it. So it's expecting, for example, a particular number of samples per second, right? So generally this is something like 44,000 hertz that it's generating samples. That is, it has, say, an audio wave, and it's going to take per second 44,000 samples, points of that, and send it off to the speaker, right? So it's sampling all the way along that, because it's digital audio, right? We're taking samples of this and sending it out to the device. And it needs to know all that information about the device, what it's expecting, so that it can, put the audio in the correct format. So that's what the config is here. The other thing the config tells it is really what shape the numbers are going to have in memory, right? This is, again, if you've not done any sort of systems level programming before, you might not be familiar with this, but essentially we need to tell the computer what format the numbers have to be in. Now these are, so F32 is a floating point number. This is a decimal number with character, numbers before the decimal point and numbers after the decimal point. So that's what a floating point number is. We've also got an integer, so this is a signed integer, so it will go from negative some value to positive some value, but it's whole numbers only. An unsigned integer is just 0 to some positive value. And depending on your system, it'll be expecting different formats for the numbers that the device will be, your operating system is communicating to the device with, right? So that's what's happening here. It's got the host system, it's found the device that it wants to send it to, the default device. We've got the config, so we can find out information about how this runs. And then once this happens, we've got a match statement, so it says, okay, what format is it expecting? Well, if it's expecting this format, run this line. If it's this format, run this line. If it's this format, run this line. And what's this funny, these pointy brackets here are telling this function information about what the type is, what the type of number it should be producing. Okay, but don't worry about it too much. Then we're sending some data to this function. The audio graph, which is going to be used for generating the sound. Again, the device, the audio device, because we're going to use that again, and config as well, the audio config, so that we can get information about how it's expecting the sound. So let's go and look at run synth now. Here is run synth. And again, go and have a look at the code in the repository, read over this. And please send me a message if you have any questions about it, right? This stuff is not, I'm new to this stuff, and it's not straightforward, right? It's complicated. So, if you have any advice or if you have any suggestions, please feel free to make them in the comments. Check down below to see if anybody's asked the types of questions you've asked before, or you can ask any new questions that you might have. Okay, so we're going to do run synth here. We're passing in the audio graph, right? This is the thing, again, it's the computational structure that's going to generate the audio information, right? Then we've got the audio device, and then this config for the audio device. And then what we're doing here, we're going to, let's put it back. We're going to spawn a thread for doing the audio synthesis and sending the audio along, right? So this is threads in programs. You probably heard that your processor is multi-threaded or has multiple cores, and it's basically a way to split up computational work in a program, right, into lots of different independent parts. Now, when you're working with audio, it's good to have a separate thread, because the main program that's running through, you don't want it to really interfere with the audio being generated or whatnot. So you want that to run all the time in the background. Now, communicating between threads, so you've got the main thread, which is running the program, and you've got another thread for the audio. Communicating between those is actually, it's non-trivial, right? So it is a very tricky thing to do correctly. This is one of the reasons that I'm using Rust, because this language really helps you to do that. And then I'm making an audio tracker at the moment. And it's where I'm having to do this and communicating between it really helps with that process. Now, we're not doing that here. We're not communicating between the threads. We're just letting the audio thread run. But we're still going to use a thread to do that. It works much, much better for generating the audio. Okay, so we've made a thread, and then it's just going to run on that thread all the code that's inside this block, right? And you can see this here. Everything that's inside these curly braces is just going to run in that thread. The first thing that it does is it says it gets the sample rate, and it sets the sample rate in the audio graph. So we say to FunDSP, okay, this is what the sample rate that my sound device is expecting. So please generate audio at with this frequency, right? So that it would generate samples when I'm asking for audio, generate it with this frequency. And you can think about that as if you've got this wave, you're cutting it up into smaller and smaller in sections depending on how often over time your computer's expecting to get audio information. Right, so that's the first thing, just set the sample rate. And again, you can just copy and paste this, right? You don't need to worry about this afterwards. But I really would recommend looking at the CPAL documentation to see what all of this is actually doing, right? And the FunDSP documentation. We're going to come back to the FunDSP documentation in a second, incidentally. Then we've got this little function here. Now, this is also a function. We've got this fun run synth, right? That is a function declaration. This is how you make a function. This is like a packet of code. But this is another way in Rust that you can define a function. This is called an anonymous function, or a lambda, or a closure. I think a closure is what they go for in Rust. But this is the way that you write another function, right? And you've got arguments would go inside these pipe symbols here. They would go in between exactly the same as the arguments go in this section up here. Take a look at the Rust manual if you want to find out more about this. There's a lot you can do with it. This move keyword indicates that basically this little function, once it's running, is going to take the audio graph and get ownership of it. That is too complex a topic to discuss here, but basically what we're saying is take the audio graph and you can go and use it, right? I'm not needing it anymore. You go and use it for whatever you're doing, right? So it takes ownership of it. Now the audio graph, and this is in FunDSP, any of these, the audio graph sort of types, so this is audio unit 64, this one's called, it has this function inside it called get stereo, and this will actually generate the samples, right? You can see here on my IDE, or my text editor, that it's giving me some extra information about what comes back from this, and this is a function, right, that is going to return two floats, right, so two decimal numbers. And this corresponds to the left channel and the right channel, right? So get stereo. And it's just a number, and that number is going to be essentially telling your speakers how, whether they should vibrate or not, right? What the position of your speaker should be. That's really what it's doing. And it's doing that 40,000 times a second, or 198,000 times a second if you've got a higher sample rate on your audio device. So that's that, but this is a function at this point, right? It's going to use this function to generate the sound from the audio graph. Then we've got the channels. So this is how many channels are in the audio, and in this case it's going to be stereo. But we can get that information from the config about what's expecting. If we send it, I think if you've got more channels, so you've got a surround sound system, if you send stereo sound, then I'm sure that'll be compensated for by your computer. I don't actually know because I've never actually done that myself, but essentially we've got how many channels the audio device is expecting. Then there's an error function, and again this is another closure. We can see an argument coming in here called error, which is going to be an error, right, a stream error, and this is defined in the CPAL library, and it's going to say, okay, if an error does occur whilst you're playing the audio, print out on the terminal that there was an error and what that error was. So that's all that's doing there. And then we have the actual stream. This is the audio stream. So we've got the device, and on that device we want to make an audio stream, a stream of audio that's coming out that we can listen to. So we ask the device to make an audio output stream, and you can have an input stream as well for microphones and other things, but we ask it to make an output stream, and this is going to be sent to the audio device, and we'll be able to hear it. And in order to build that, and let's go to this is the actual definition of this function here. This is the code, which is on my computer currently, because I'm building this thing, so we can take a look at it. This is what it's expecting, and it's expecting the config, a callback. So a callback is another name for one of these anonymous functions that we can pass into. It's a function that will run when it's trying to get data to send to the audio. The error callback, and then a timeout as well. So this is, this would be This is an optional type, so that means that it can either have some value, like say 5 seconds, or nothing at all. So it's gonna, it'll just ignore it. None is the type. And if we go back, we can see here that we've said there's no timeout. Just play the audio and keep on playing the audio. Now, this returns, this function, the build output stream. And again, if we go to the definition of it, you can see it's returning this thing called result. And then it will either return the stream or an error. Right? So result tells you that this might fail, it might go wrong. And there's lots of reasons that it might go wrong. Probably that there's something, it's tried to negotiate making an output stream with your device, and your device said no, that it's not allowed to happen. And if that happens, we just want it to stop, right? In this case, in a more complex program, you might want to handle that. And based on the error, you might want to give some information. It's like, oh, sorry, we could not connect to your audio device, or this thing was blocking it, or who knows what the reason is. But in this very simple example, all we want to do in that case is go, well, just panic, just say, okay, this failed, and then we'll print out that it failed. And this is what we're using here. This is unwrap. It will take that error, and if it was successful, it'll return the stream, and if it's not successful, then it'll just crash. Okay. Then we take the stream, and then we play it, right? And it will use that callback, this one up here, this next value callback. Well, we've got this, sorry, actually, it will use this callback here, this function here, which is using this next value callback here, which will actually generate the audio information. And this write data function, we're going to talk about that in a little second, exactly what that is and what it's doing here. These T, don't need to worry about them. This is just saying that we're going to have an array of numbers which are of the type that have been defined up at the top. Remember, I said that your computer might be expecting a 32-bit floating point number or a 16-bit unsigned integer or something for the audio data. And so we don't know what that type is, but when we compile and run this, we will know, and so it can compensate for that. Well, actually, when we run it, it will do this. So it's just saying that there will be an array of numbers, and it's a number that we can handle, so it's fine. And then you're going to run this thing. So we're going to have this data, which is an array of numbers, and we're going to have a number of channels, and we're going to use this next value to generate this. We'll talk about write data in 2 seconds. So once we've got the stream and it's established, we can play it, and this will generate the sound. And at the very bottom of this, we have a loop. And this means that this thread, remember, this thread is independent from our main thread that we started on. It will just loop around forever. Now we do not, if you didn't have this, if you just had this loop and it was totally empty, this little function, this thread, would hammer your CPU, constantly polling it and, checking to see what's going on. It would do this very fast, and it would use up a lot of resources. If we put a very short delay here, right, so it's 1 millisecond where it's not checking anything, it's not doing anything, so it just puts it to sleep, then it won't hammer your CPU thread. And the audio stream won't be stopped by this, right, because it's independent. It's at the level of your operating system. It's made this audio stream and it's running in the background. In an actual application, you could check for stuff like here, like input or updating values or something. You could poll it every millisecond or every, microsecond or something like that, however frequently you need for your application. Okay, so that thread is running. Now, when we run this function, the main thread will make the thread, it will get to the bottom of this and then exit, and it will return back to the main. Remember, it's independent. This thread is independent, so it will return back up here. And this is why we need this pause in this section here, this 5-second delay, because if we didn't have it, it would get to the end of this and it would exit. The program would finish, and that would be that. You wouldn't hear anything. So we had to delay it. And then the audio stream, so that this thread that's doing the synthesis and the audio stream, we can hear what that's doing, right? So we're just waiting for 5 seconds here. You can change the duration of this. You can have 10 seconds if you have a very long and evolving sound, or make it 1 second if you don't need it as long. Right, okay, so that is the sort of run synthesis function. The last part of this puzzle is the write data function. Oops, I pressed that button again. Is the write data function. And this is actually taking the data from the audio graph, from FunDSP, and writing it to the part of memory that your computer is expecting the data to send to the audio, right? And this is handled for us by CPAL again. We've got our output, which is an array. This is like an immutable array of numbers that we're using in order to, we'll get this, and this is the place that we're going to write the samples into. And then we've got the channels, number of channels, because we need to know, like, if we've got a left and a right channel, or if it's just mono, for example, or, I suppose if it's like 5.1 surround sound, if it needs to know how many different channels it would be expecting. And then it has this little function, next sample, which will take, it's using our audio graph to generate the samples it's going to be actually writing to this region of memory, which we'll then hear. So iterates through chunks of this output buffer, right? This output array. It iterates through them, and then it generates the sample using this little function. So this is the actual floating point numbers. It assigns the type of this, so we can take that sample and then we can convert it to the right sound type for our audio device. So this is what this T is. Remember that we're up at the top. It could be a 32-bit floating point number. It could be a 16-bit unsigned integer. It could be a 16-bit signed integer. This is essentially saying that we don't know exactly what it is, but it's going to be one of these types that we can handle, right? And so it will generate this. And this is the left channel, so the first part of it, because there's two numbers in this, the first one will be, which is the 0th one, will be the left channel, the 1th one will be the right channel. And then we take this little chunk of memory that we've got, and we can actually write the sample to that bit of memory, which will then be played through our audio stream. So you've got channel and sample here, we go through that, and we write the first one and the second one, and all it's doing is checking to see if the channel is equal to this is to 0, then it's the left channel, otherwise it's the right channel, and it just writes this to this point. And it just does this over and over again, very, very, very quickly. Now, I didn't write this code. This was taken from, I think, either a mixture from CPAL and the FunDSP examples, or maybe just directly from the FunDSP example. But this is kind of like the sort of the infrastructure that we need in order to listen to the sound. But let's get to the fun stuff now, right? The actual audio synthesis. Probably the reason that you clicked on, or I imagine the reason that you clicked on this video, right? Now, you can learn the maths associated with sound waves and what they're expecting. You can do this relatively easily yourself. I mean, you could get a sound out of your computer relatively easily, right? But what FunDSP enables you to do is to do this in a much more complex way, and to be able to do audio processing of all different types and combine things together in a really simple way. Now, when we first started this video, I played you this sine wave that's at 440 hertz, right? It's an A4 on a MIDI keyboard. So it just generated this. And the way that I did this is using this sine hertz function, which comes from the FunDSP library. Let's go and have a look at that in our browser. We can find them where that is. Let's go with sine hertz. Now, one thing I'd really recommend looking at here is it's this README that's at the front of the FunDSP GitHub page. Again, there'll be a link in the description to this, to the repository, and it'll have all this information here. And what this does is it's expecting, so you can see sine hertz here, this really has lovely documentation in this README, and it's actually quite readable, although it's complex because DSP is complex, or digital signal processing is complex. But you can see here that we've got sine hertz and a frequency. And then it has, if we go up here, we can see that this is talking about the, if we go, oh man, it's much further up. There we go. This is the function. So the function that we're using to generate sound, inputs and outputs, and then the explanation here. So let's go here. And we'll go back to this one. So it has no inputs to this, right? So it's not expecting any numbers in to control this. And we're making a graph. We're connecting together lots and lots of sort of audio sources and ways of modifying those audio sources and combining them together. This is what we're going to be doing. And you can see here that it has no inputs for it, and it's got one output, and that is it's going to be an oscillator that's oscillating at a particular frequency. In this case, we've said 440 hertz, and it's going to generate samples along that sine wave, and we can then send those off to our audio device, right? So that's what this is doing. It's got no inputs and just one output, and it's just making a number. It's making a pair of numbers because it's stereo that's going to be the sine wave at particular points as you're sampling along over time. Right, so let's have a look at that here. So this is really simple. And this is the audio graph. And every time that you run that get stereo function, it'll return those two numbers, right? Two floats at the appropriate point after a particular point in time. And it keeps track of the time that's passed, and it can send the appropriate number, and it'll keep track of all that for you. So this really is the sort of simplest one, and can just generate sounds from it, and it'll be at just a tone, right? Let's play it again in order to, and I'm going to make a new tab here. I'll make this a bit bigger. Hopefully that is, and then we're going to call directory into this example. Okay, and I'm going to just play it again for you. Cargo run release. Sorry, I should have gave you the warning that it was going to be very loud. So that's all it is there. Right, so let's make a more complex example now. Now, if you go up to this function here and you change this, we can change this to create C major, right? And you can probably guess what's going to happen here. I've just saved the code there. And this is the function here. Now, what we're doing this time is we've got a sine wave, just the same as before, but we've got a frequency for a C, and then we've got a frequency for an E above that, and then a G above that. So it's a C major chord. It's a C major triad. There's 3 tones over the top of each other. This time, instead of just going get stereo, right, when it's actually generating the audio up there, it's first of all, it's adding these together, and then it generates the sample. So if you've got different sine waves, each with different frequencies, if you add them together at a different point, it makes a more complex sine wave, and that more complex sine wave sounds like your C major chord here. Now let's have a listen to that. We can go to this other tab again and run it. Very nice. Got this nice harmonious C major chord, right? And that's just by adding them together. But this is magic, right? How can we even plus these things together? Well, let's go back and take a look at the documentation again. If we scroll up, and I'll probably use the bar here because it's quite far up, we can see these operator diagrams. Now, you can see in these diagrams, here's some. This is the one that we're interested in this case, right? We've got 2 or more audio sources, right? And we've got 2 audio sources and we want to add them together, right? So what we've done here is we've got a sine wave up here. This is like our first sine wave, and another sine wave here, and we're going to add them together, right? 2 independent sine waves. So each sample that we're generating, we generate the sample and we add it together, and then we take the summed sample and then we send that out to our audio device. Now, then we've got a summed one, and then we have a sum on top of that, another one. So this would be, for example, to start with our C and our E, we sum those together, and then we pass it into another summing function, which is going to take the summed C and E and then add a G to it. And then when you sample that, it'll be the chord, right? So lovely. This is how it works. You can add these sine waves together. You can add together all types of different waves in order to get the sound combined, right? So let's change over to our terminal again. And you can see here that I've got some other ones underneath. They're using different, let's comment this out. We don't need to, but we will because it's a bit clear. Let's try it with a square wave. Now, again, let's go back to our browser and we can search for square. And you can see that there's this square and square hertz. Square hertz, you give it a defined frequency, and then it'll generate samples as time changes, stereo samples at that particular frequency with a square wave, right? So let's run that and see what it sounds like. And you could probably guess. Oh, no, I have not saved it, I don't think. Because that does not sound like a square wave. Let's try again. There we go. So instead of that nice smooth sine wave, we've got a kind of angular square wave, and it has this lovely, like, it reminds me of the NES or the Game Boy. These kind of square waves got that kind of buzzy sound to it. And you can, this is the joy of FunDSP. So you can play around with these different types of oscillators, because these are oscillators, right? A sine wave oscillator. We've got a square wave oscillator. We've got other types as well. Let's try another one whilst we're doing. We've got soft saw, for example, here. And we can play that. Yeah, I really like this one. Yeah, I think soft saw kind of, again, instead of it being a smooth sine wave or a sort of angular square wave, this is like a sawtooth, right? That's going up and down like this, and so it has this kind of buzziness. And I don't know what the soft is in this, but there's obviously some algorithm that the writer is using here to get a soft wave. I don't know why it's called that over just a saw, for example. I think there might be just a plain saw, but this is one. Band limited soft saw wave. This is what it's called. We've also got Hammond. This is a Hammond oscillator. It says something about it picking out particular. Let's find the documentation for it. Search for Hammond. Yeah, Hammond here. So Hammond Hertz is the one we're using, where we're using a defined frequency. And this one is the one you can use to send it a particular frequency information so you can make a live interactive synthesizer. But band limited Hammond oscillator at a particular frequency emphasizes the first 3 partials. I don't know what the first three partials are. I imagine that they are particular overtones over the pure tone itself. But I just don't know that much about DSP. I'm learning at the moment. If you do know, you can please enlighten us in the comments. I would appreciate that. So let's save this and then see what the Hammond organ oscillator sounds like. As you would expect, right? Very nice. So there's lots of different oscillators, and the oscillators are kind of generally your kind of entryway. This is the first audio source that you're going to be having. You can sum them together. You can also, if we have a look at some of the other operators here, let's go up to the top again and look at these. You can mix them together in different ways. These ones are kind of taking two and mixing them together. So you've got different, so we can subtract them away from one another, and you've got product. So you could do some really interesting stuff here to mix together different oscillators and in different ways. So we've got the product, so you can multiply them together as well. Lots of different effects, and of course there's lots of things that you're wanting to do. Product's also very useful for making volume control when you've got a parameter that you can change interactively. I'm not going to cover that in this video, but I might in a future video if people are interested. But for example, you can multiply it by a number between 0 and 1, and then you can say 50% volume by multiplying it. And I'll actually give you a little example of that in a second of how you can do that. Then, so you've got these operators, right? We're summing them together, and we've made this new audio graph by mixing together these different oscillators or different elements of the audio generating graph elements. But you also have these are for sort of, these other operators do something different, right? They don't just add and subtract things. They're very useful in different ways. We're going to use, in particular, we're going to use stack, and we're going to use pipe. What pipe does is it takes the output of one unit of the audio device, so like say the oscillator, and puts it into another device, right? Another audio unit. So it's going to send that in. So then the numbers from the sine wave are going to be put into something else. And we can do this to make more complex sounds. And then stack as well. It's like you take two things, two, say, mono channels, for example, you stack them together in order to make a stereo channel that you can then pass into something that's expecting stereo. But you can do lots and lots of other things with this. So take a look. There's good documentation here that kind of explains some of this. So let's look at another example. So here we go. You might want to play a sample, right? This is a thing that you might want to do, and I've included a really simple little closed hi-hat sample in this code repository. And then we can play it here. It's not, maybe it's slightly more complicated than the other one. I'll talk about what the arc is in a second. First of all, we need to load the wave, right? We've got a WAV file. We want to load it up. And what we do is we go into the samples folder, and this is the name of it, and it's going to load this up. And, I'll just show you. This is here. If you go ls samples, there is closed hi-hat. You can see it here. And it's going to load up the sound information for that, right? It's a WAV file. It's going to load that up. And then we'll expect that there could be an error here, right? Because this is going to return, let's see if we can go to the definition here. Yep, so it is going to load, it's going to return wave result. So remember I said before, like the result can either succeed or it might fail. And one of the reasons it can fail is that it just couldn't find the file. So we're going to say we are going to expect that this could fail, and it might not have found the file if you give it the wrong path. So if you change this here in code, it might not find it. But of course, you can also just use any sample that you like. This is a very short closed hi-hat. Then we're wrapping it up in something called an arc. Now, I'm not going to explain in too much detail what this is, but it's basically for managing shared references to something. So shared, we want multiple things to be able to access this at the same time. We want to be able to pass it around. And a safe way to do that is using something called an atomic reference counter, which basically records how many things are using this currently. This is just what we need in order to do the next section, which is this wave64 function is called a wave player. It makes a wave player, so it'll take a wave file, right, that we've loaded in from disk, and then it will play that. But it is expecting that wave to be passed to it as it wrapped up in an arc, right, an atomic reference count. So again, we can go to this here, and it's just expecting that this is, wave 64 is going to be there. Okay, so we've got two wave players, one for the left and one for the right channel. We're saying the zeroth, which is the left channel, and 1, which is the right channel. And then it also accepts a loop point. And it's an option again, so it might have no value, in which case it's none. So it's not going to have this be looping to start with, but it can also have sum, which is a loop point. So if you said sum 0, then it'll loop at the beginning. And I'll show you that in a second. Now, we want to take those left and right, and we want to combine them together because we want to use get stereo, right? So we need to have a stereo sample. These are mono at the moment. If we stack them together using this pipe, well, I call it the pipe operator. This is what you'd usually call it, but it's kind of confusing this. It's called the stack operator in FunDSP. You can stack them together, and then now you've got a new audio graph that generates stereo samples, right? So you can work with stereo samples like this. And then now it's a new audio graph, right? It is an audio unit here, audio unit 64, and we can use get stereo to get samples from it. So let's have a look and see what that's like. We need to go back up to the top here, and we're going to do create sample, save it, and then we're going to go over here, and then let's run it. Right, it's quite short, so hopefully you can hear it. Right, I'll play it again because you might have missed it. It's gone for 5 seconds, but it only lasts a very short period of time, and it's not looping. Right, here it comes. There we go, like a little hi-hat hit. Right, so I'm sorry, I wanted to keep this sample small so I could put it up on GitHub and people could download it without having to use huge amounts of space on their computer. But it is quite short. But I can make it longer, right, by looping it, by giving it a loop point. So we're going to say sum 0. I want it to loop from the beginning. And I'm only going to do it with the left channel. So you should only hear in your left speaker or left headphone it looping, right? And then we can go back and run this again. Hopefully you can hear that this time. Funny buzzing because it's a very short sample and it's just looping over and over and over and over again as soon as it's finished. So we can put a loop point like this. And actually there is I think it's called Wave64 at, where you can change the start and the end point of your sample, right? And this is, again, it's just generating audio from that sample. It's just going through each sample that it has, and it's taking each of those samples and it's sending it off to your audio device, right? It's just some file. FunDSP also has functions for writing WAV files. So you can make an audio graph and then you could say, okay, sample 5 seconds of it and write it to disk. So you can use it to generate samples that you then use in your sampler, your SP404 Mark II. You can make your own samples here. I'm not going to show you how to do that, but there's documentation. You can take a look at the documentation in order to do that. Again, if you're really interested in a video about that, please leave a comment down below and I'll see what I can do. Okay. So that is create sample. Now, these are still quite simple graphs, right? We've done adding together a few different sound waves. We've also got stacking on top of them, a left and a right channel. Let's do something a little bit more complicated here. We've got create sample with reverb, and you can guess what happens, right? This section is all exactly the same. We're just loading up that hi-hat sample. Then we've got the left and the right channel, and we're stacking them together. So this is a stereo sample that's coming. Then what we're doing is we're piping in, we're taking the output of that one. It's generating audio data, left and right channel, and we're going to send it into another audio graph. And this audio graph is expecting, it's sort of stacked on top of each other with this bus operator, this and here. Part of it is that it's going to have multipass, so it's going to pass through that channel information. So one side of it, when we're stacking these on top of each other, is going to just send the audio straight through, and the other one is going to be sent to this other one. So this is one part of the graph here. So you're going to pass the audio straight through, and this one is going to send it to reverb stereo. So we're going to take those stereo samples from left and right and send them into reverb, and then we're going to add some reverb to it, right? And we've got this number here. We're going to multiply the reverb sound by an amount. In this case, 1. So we're going to get like the full effect of the reverb on the audio, right? And then this is getting mixed back together again. So we've got this coming out. We've got using this ampersand operator here, which is bus. We're going to separate them out, and then they're going to get mixed back together at the end. Okay, so it's sending this, but it's sending the same data from left and right to both the multipass straight through and to the reverb. Let's have a look and see what that sounds like. Okay, and we'll play this. Let's see. Cargo run release, and you should hear it now. Ooh. Lots and lots of reverb on that, right? And you can tune the reverb parameters here. Now that's that again. Let's go back here and just have a look at how that works. So in this, we've got in this reverb stereo, and again, you can find the documentation on that front page there, or in the actual cargo docs as well. You can find them online or read through them. You've got reverb stereo, and you've got room size, which is one of the parameters this takes, and then time, the decay time of the reverb, right? And we can also add less here. So again, this is just taking this is a graph, right? So this is generating audio samples, and we know that we've got that multiply operator, so we can just apply a value to it. So let's take 0.2% of the reverb, 20% of the reverb we're going to have in this case, and I've saved that there, and you'll hear hopefully less. It's dry, right? There's less of the reverb. Yeah, so hopefully the reverb you could hear there was quieter. I'll play it again as soon as it's finished, because it does 5 seconds. There we go. Right, so that sounds pretty good. So you can tune the amount of this one that's then getting merged back together after the bus, right? After it's going left and right, bussing out, you've got the multipass, you've got the original sample, that's retained. Or you wouldn't need to have that. You could have a pure wet signal if you wanted, so you could multiply multipass by 0, and then you wouldn't have anything. You could have a proper wet dry mix. And it's going the other side, it's going into the reverb and out. And of course, you can have other effects. There's things like chorus, there's delays, hundreds of different types of delays. There are filters for filtering particular type of audio. I'm giving you sort of really simple example here that are hopefully easy to follow. Okay, so the final example that I'll give you is, and this comes directly from the FunDSP documentation, is a simple FM synthesizer. And this shows you a slightly more complex audio graph, right, that you could do. And this is not a tutorial about FM synthesis. It's very complex. It's sort of magic to me. I still don't understand why it makes such interesting sort of sounds, but it does. So, you can, there are videos explaining this. Hopefully I will be able to get my head around it one day. But if you want to make a little simple FM synthesizer using this library, you can. Now, what we have here is, when we're defining this, we define a frequency, right? This is 440 hertz again. We have a modulation index, M, and we're going to use that in order to make, from a simple sine wave, we're going to make a more complex sound wave, right? Like we're going to modify its frequency. This is frequency modulation, right? We're going to modulate its frequency in order to be able to make a more complex audio wave, right? With different, there's just that smooth sine wave, right? It is, different tone to it. So we start off, we're using the sine hertz function again at a defined frequency, so it's 440 hertz, and then we're multiplying that by the frequency again. So this is generating a sine wave between -1 and 1 with a frequency of 440 hertz. Then we're multiplying that by 440, so it'll be going between -440 and +440. Then we're going to multiply it by this modulation index. So that's getting times by 5. So that's going to, I won't do the maths, but it's around 2,500, right? Plus and minus. And then we're going to add the frequency to it as well. So everything's going to get shifted up by 440, right? And then what we're doing is we're not listening to that sound directly. We're using that to modulate a sine wave, right? So we're passing it into this sine function here, also from FunDSP. Now notice that this is sine hertz, which is a sine wave at a defined frequency, and this is sine, which takes an input which tells it this is the frequency that you should be oscillating at. So we're going to change the sine wave's frequency based on this more complex wave up here, right? So we've got a sine wave that's modulating the frequency of another sine wave. And that's why it's frequency modulation. So if we look at the documentation here, you can see this is sine hertz, so that's a defined frequency, and this is the sine one. You can notice that the input here is it's expecting one number in as the frequency information, and it's generating one number out. So we're generating the frequency information in this little graph here. I'll show you on here. This little graph is generating the frequency that is then getting sent into this sine function. Incidentally, this is how you'd make an interactive synthesizer as well, where say that you're waiting for MIDI notes and then you're sending a frequency into, say, a sine wave oscillator, and you're changing it based on key up and key down information, right? But this is also how we're doing this to do FM synthesis. So let's have a little listen to this and see what it sounds like. Yep. so you got that kind of metallic sound that FM synthesis, it's sort of associated bells and sort of jarring, but also you get some very strange sounds. Now, obviously, this does not have an envelope, which usually you would have to modulate the the carrier, no, the what do you call it? The operator. So you have the operator usually consists of this wave that's changing the frequency and then an envelope as well. But that's, you can also do that with FunDSP, and you've got envelopes and other things like that. So this is just a wee overview of some of the things that FunDSP can do. I just think it's a really nice library. I think that it's fun to use, and you can start playing around with ideas for synthesis. And you can recreate and this is the first thing I did, you recreate your favorite synthesizer. I think that it's sort of easiest to start with an analog synthesizer, Google it, find out what the signal path is like, and then build it up using FunDSP, and then you can generate some sounds with it. And like I said, you can also, using FunDSP, write the wave to a WAV file, and then you could load it in and use it in another, a sampler or whatnot. So you could use this to actually generate some interesting sounds, and you can play around with audio synthesis. Now, thank you so much for listening. If you have any questions, please don't hesitate to ask in the comments down below. And please share anything that you make that you think is interesting. And like I mentioned, I'm using this to make an audio tracker at the moment. And it's been a lot of fun. It's been pretty challenging, but it's been a lot of fun. And I'll share that soon, hopefully. And I'll share the source code for that, and you can have a look around and see how I've done that. And that's more interactive, right? We're changing, rather than just making a set sound, we're changing all sorts of different things. So again, thank you so much for watching. If you found this useful, please like and subscribe. Please feel free to ask me any questions you have down below. I'll answer them if I can, or try and point you in the right direction if I can't. But this is Chris from Oak Creek. Thanks again for watching, and hopefully I'll see you at the next video.